Hello everyone, and welcome again to this session on NPTEL's course on Essential Mathematics for Machine Learning. So, as all of you are aware, that we conduct these sessions every Saturday, where we solve the previous year's assignment problems corresponding to the week that is going on. So, this is week 9. That's why we are solving assignment 9 from the previous year. And these previous year's assignment problems would help you solve the current session's assignment problems as well. So, as always, I would just put up the links in the chat box, the links to the YouTube channel, which you can go and subscribe. And then we have the Google Drive link where all these lecture notes are uploaded. So you can just bookmark these links and save it for your future reference. So each of these sessions that we have are recorded and live streamed on YouTube. So you can basically go to YouTube and revisit these questions as and when you feel like. So I have put up the links in the chat box. So go ahead and save those links and subscribe to the channel. So let us start with this week's assignment problems. So this is week 9. We are looking at assignment 9. And let us look at the first question. So the first question says that the point minus 2 over 13, comma 10 over 13 for the function fx, comma y is equal to x squared plus 3xy minus y squared minus 2x plus y plus 6 is, and we need to select whether this point for this function is either a point of minima, a point of maxima, a stationary point, or not a stationary point. So let us start solving. So condition for a stationary point is gradient of f equal to 0, and gradient of f equal to 0, which implies gradient of f is what? Del f by del x and del f by del y. So this is equal to 0. So this implies that individually all these terms are 0. So this implies gradient del f by del x is what? It is 2x plus 3y minus 2, which is equal to 0, and then del f by del y is also equal to 0, which implies 3x minus 2y plus 2 equal to 0. Now if we substitute this point, in these equations, then what do we get? We get the following. Just simplifying, which is indeed equal to 0. So it satisfies the equation. Then if we look at the second equation, sorry, something I have done wrong. X minus 2y. So this is minus 2y. So this should be minus 20. So this is also equal to 0. So this also satisfies this equation. And that means that gradient of f is 0 at this given point. So it is definitely a stationary point. Now we need to check whether it is a maxima or a minima. For that, what we do is we find the del squared f. So del squared f is what? So yes, so now this is the del squared f matrix. We need to check whether it is positive definite or negative definite, and we will use the minor test to do so. So minors of order 1 cross 1 are what? 2 comma minus 2, and minors of order 2 cross 2. So minors of order 1 cross 1 are simply the diagonal elements. This is simply diagonal elements, and minor of order 2 cross 2 is simply the determinant. Now, since these minors are basically minors of order 1 cross 1, one of them is positive, one of them is negative. So that means this is indefinite. This is an indefinite matrix. Had both of these minors been positive, had all of these minors of 1 cross 1 order and 2 cross 2 order had been positive, then we would have said it is a positive definite matrix, but some are positive, some are negative. In that case, this is indefinite. That means it is neither positive definite nor is it negative definite. So if it is indefinite, that means this point is neither a maxima nor a minima. Why? Because for minima, del squared f should be positive definite, and for maxima, del squared f should be negative definite. And if del squared f is indefinite, then it is neither maxima nor minima. So as a result, option C is the correct answer, that the point is a stationary point. It is stationary because del f is 0, but it is neither maxima nor minima because del squared f is a basically indefinite matrix. Now let's move to the next question. Consider the problem minimizing of z equal to x squared minus 2xy plus y squared minus x plus 2y such that, so it is under this constraint that 2x plus 3y less than equal to 6 and x comma y both are greater than equal to 0. If the point x not equal to 0 and y equal to 0 as well as lambda equal to 0 satisfies KKT conditions, then we need to find out the value of x. So now before proceeding, let us write down what the KKT conditions are. So for KKT conditions, we have the problem of minimizing f of x under the conditions that gi of x is less than equal to 0. So these are the constraints, and we can have m such constraints, and both f as well as all the gi are functions from Rn to R, and they are continuous and differentiable. And so KKT conditions are given as follows. So let's say x bar is a point of local minimum. Then there exists certain multipliers lambda I. So again I equal to 1 comma 2 up until m, and these are basically KKT multipliers or Lagrange multipliers. Then what we have these following conditions that these need to be satisfied. So these are necessary conditions. This first condition, then this is the second condition, then we have the third condition, and finally the fourth condition. So these are the KKT conditions. So KKT conditions for a point to be minimum. So this is necessary condition. So these are important. These are our KKT conditions. So let us highlight it and keep it with us. So now we need to look at our given function. So we are given that the function is as follows. And then these are the constraints that we have. So three constraints we have. So according to the KKT condition, let's say the first KKT condition that we have, it says that gradient of f plus lambda times gradient of the constraints, sum of that should be equal to 0. So this needs to be equal to 0. So gradient of f is what? It is 2x minus 2y minus 1. And this is del f by del x, and del f by del y is the following. Gradient of g is 2 and 3. Gradient of h is simply negative 1 and 0. h1 that is, and gradient of h2 is 0, negative 1, and this should be equal to 0. So this implies this is the first equation, and second equation. This is the second equation. And also from the third KKT condition, we have this one, this lambda gi equal to 0. So this gives us lambda g1 equal to 0, mu1 h1 equal to 0, and mu2 h2 equal to 0. So putting in the expression for g1, now we know that x is not equal to 0, which implies mu1 should be equal to 0 from this one right here. And we are also given that y is equal to 0 and lambda equal to 0. This is given to us. So now we will look at this first equation over here. So 2x minus 2y minus 1 plus 2 lambda minus mu1 equal to 0, which implies 2x minus 0, y is 0, minus 1 plus 0 lambda is 0, and minus 0, mu1 we found out is 0. So this gives us what? This gives us x equal to 1 by 2. So we have found out the answer. We need to find out the value of x equal to 1 by 2. And if you want to find out the value of mu2, you can do that from the second equation. Although it is not asked, but still we can do it for the sake of completion. So x we just found out is half. So like this. So this gives us that mu2 equal to 1. So although it is not asked, we can still do it for the sake of completion. Next question. For the QPP of in the form minimizing. Ma'am, how do we know lambda is for first GI? Oh, this is just that we are setting it the way we are defining the stuff. So this is that basically this is how the convention is taken. So typically you would have functions of two variables. Like, so this is the convention followed in this lecture series that we are having. So if you look at your course, then the convention that is being followed in the lectures of this week, if you see, then it is typically taken lambda for the first condition. First condition meaning the condition which is most significant. If you look at this condition, x comma y greater than equal to 0, well, this is a condition, but this is like a very trivial kind of condition. It just says that things need to be positive. But if you look at this condition, then this is a little bit more specialized kind of condition. So it says that 2x plus 3y should be less than equal to 6. So not just positive, but it should also follow this kind of a relation. So typically in this course, the convention that is being taken is that lambda is for the first condition, which is the most significant condition, meaning conditions other than stuff being positive. So this one is this one they take as basically functions h1 and h2, and this they take function as g. This is basically convention. You can take whatever convention you want, but you need what is important is that this equation needs to be satisfied. So whether you call this thing lambda or alpha or beta or whatever, this equation needs to be satisfied. So you have three conditions and you have one function. So gradient of the function plus some multiplier times the gradient of the constraints and sum of this. So multiplier times gradient of the constraints, sum of these should be equal to 0. So this is the constraint. This is from the KKT conditions over here, the first KKT condition. So yeah, whether you call it lambda, whether you call it something else, that's totally up to you. In this course, the convention that is being used is that lambda corresponds to the first significant condition that we have, and then we have mu1 and mu2 for the other conditions, which are basically saying that things need to be positive. So if you get a question, then you should follow this convention in this particular course. Otherwise, the concept remains the same. The important thing is this equation right here. So this is the main thing over here. So once you understand this concept, then you can solve any question, no matter what the convention is. So let's move ahead. Yeah, so this, we have a QPP in this form, minimizing half x transpose qx plus c transpose x such that ax is less than equal to b and x is greater than equal to 0, and minimizing this function. So we are also given this function. So this is the general form of a QPP, and we are given that QPP is minimizing fxy equal to 2x squared minus 2xy minus 2x plus 4y squared minus 3y such that 3x plus 2y is less than equal to 6 and x and y both are positive. So QPP means what? It is quadratic programming problem. Again, I am not a big fan of short forms because I don't like short forms. They just make things so much confusing. So QPP means quadratic programming problem in this course. Maybe in some other course you are using some other short form for something. So yeah, over here it means quadratic programming problem. So let us see what the question is. Question is asking you to find out this Q and this C. So it is very simple. So we have fx comma y as follows. So this is my function, and we can rearrange it as follows. So we can, since we need to convert things into this kind of a form, so we need half over here. So since we need to decompose it into this kind of a form, which has a quadratic term in the form of x transpose qx, and then a linear term in the form of c transpose x, that's why I'm trying to separate this function, rearrange this function by clubbing terms of the quadratic form in one bracket and terms. So this is the first term, which is of quadratic form. These are the quadratic terms, and these are the linear terms, just separating it out. And then half over there, because this is how we are defining our quadratic programming problem, with the half in a prefactor in the front. So let us just now write it. So now we are putting it in the matrix form. So you see that this linear term we have written in the matrix form as like this. So it is true, it is minus 2x minus 3y, and this quadratic form is coming over here. So we need to write x transpose x. So this is x transpose and this is x, and then this matrix q in the middle, and this is c transpose and x. So from this you can clearly see that q is nothing but 4 negative 2 negative 2 8, and c transpose is this. So that means c is what? C is the column vector negative 2 negative 3. So the correct option is option C. Now we will look at the next question. So this question is, let f be defined as a function from the interval minus 3 comma 10 to real numbers, and let this f be a unimodal minimum function with f1 equal to 5 and f5 equal to 1. Then the point x min lies in which interval? We need to find out. Now, from the properties of unimodal functions, so unimodal functions are functions which are defined from an interval a b to the real numbers, and they can because it is unimodal, they contain only one peak. Now this one peak in the interval a comma b, and this peak can be either minimum or maximum, like a point of minima or a point of maxima, and this interval is called interval of uncertainty. Then for a unimodal minimum function minimum function meaning now we will look at min. So this peak needs to be a minima. So unimodal minimum function, so you have x which is bit in that interval a comma b, and f is strictly decreasing in a to x, and f is strictly increasing in x to b, and then this x is the point of minimum. So x is the point of minimum that we have. So this will be the unimodal function. Now if we have 2 points x1 and x2 in the interval like this, and if we have f of x1 less than f of x2, then the x min lies in the interval a comma x2 if f of x1 is greater than f of x2, then x min lies in the interval x1 comma b, and if f of x1 equal to f of x2, then clearly x min lies between x1 and x2. Now in our case, we have what? We have x1 equal to 1, x2 equal to 5, a equal to minus 3, b equal to 10. So what we have, f of x1 equal to f of 1, which is equal to 5, and f of x2 is equal to f of 5, which is equal to 1. So we get f of x1 is greater than f of x2. Okay, so that means this condition. So which implies x min belongs to x1. x1 is 1 and b is 10. So in this interval. So the correct option is option D, the interval in which the minimum of the function lies. So let's move to the next question. Which of the following is a convex programming problem? So we are given 4 functions with certain constraints, and we need to find out whether these are convex programming problems or not. So a convex programming problem is one in which for minimization type programming problems, it is convex if f is convex, and f convex means that del squared f is positive semi-definite, and if it is a maximization problem, then f should be concave. Concave means that del squared f should be negative semi-definite, and g needs to be convex always, and linear functions are always convex. So linear functions are definitely convex. So all these constraints that we have are linear functions. If you look at it, all these are linear functions, and so all these linear functions are definitely convex. So we now need to look at the function and see whether the function is convex or concave, and decide whether it is convex programming problem or not. So let's start with A. This is the first function for option A. Now del f gradient of f is as follows. This is gradient of f, and then we need to find out del squared of f. This is a minimization problem. Problem A is for minimization. So this is my del squared f. Now we need to check whether it is positive definite or not. So minors, we will use the minor test. So minors of order 1 cross 1 are 4 and 2, which is greater than 0, diagonal elements. And then minors of order 2 cross 2, it's the determinant. So determinant of this matrix is negative 20, which is less than 0. So this is not positive semi-definite. So it is a minimization problem. So we need to check whether del square f is positive semi-definite, and it is definitely not positive semi-definite because the minor of order 2 cross 2 is less than 0. Let's look at the second function. So f of x comma y is equal to 6xy minus x squared minus 4y squared. And then del f we will find out like this. So let me copy this stuff from here. And this is a maximization problem. So what is del f? Del f is and del squared f. So now again minors of order 1 cross 1 are negative 2 and negative 8, the diagonal elements which are less than 0. Minor of order 2 cross 2 is the determinant. So this is minus 16. So no, this is 16 minus 36. So this is negative 20. So this is less than 0. So again, this is not negative semi-definite because for maximization, we want a negative semi-definite, but this is not negative semi-definite. Why? Because for negative semi-definite, minor of order 2 cross 2 should be positive. Minor of order 1 cross 1 should be negative, but minor of order 2 cross 2 should be positive. So minor of order 1 cross 1 is negative, but minor of order 2 cross 2 is also negative. This should have been positive for it to be negative semi-definite. Now let's look at option C. This is the function. This is a minimization problem now. So let us find out this gradient of f. And then del squared f. So minor of order 1 cross 1, this is 4 and 6, so this is greater than 0. Minus of order 2 cross 2, this is the determinant. And this determinant is 25, which is positive. So this implies that we have a positive semi-definite matrix. Del squared f is positive semi-definite, which implies that f is convex. And if f is convex and it is a minimization problem and G is also convex, then we have a convex programming problem. So option C is the correct answer because f is convex. And why is f convex? Because del squared f is positive semi-definite and the constraint is also convex because we have only linear constraints. Just for the sake of completeness, we will look at option D, although we have already arrived at the correct answer. The correct answer is option C. But still, for the sake of completeness, we should check the last option as well. So this is a maximization problem. So del f is as follows. And you can clearly see that this is an indefinite matrix because why? Minors of order 1 cross 1 are 2 and minus 2. So this means it is indefinite because one is positive and one is negative. And if you look at minor of order 2 cross 2, negative 4, but this is inconsequential because in the minor of order 1 cross 1 itself, this matrix has turned out to be indefinite because some of the minors are positive and some are negative. Moving over to the next question. This is a pretty longish kind of an assignment, so yeah, means the questions are a little bit lengthy in this assignment. So next question is, using steepest descent algorithm, the value of the function fx equal to 2x squared plus this capital X means x comma y. So f of x comma y is 2x squared plus 2xy plus y squared plus x minus y, and we need to find out the value of the second iteration, the value of the function at the second iteration, starting with some initial guess which is 0 comma 0 using the steepest descent algorithm. So steepest descent algorithm is an algorithm to give us the minimum value of a function. So this is the function. We need to find out the minimum value of this function, and for that we will use the steepest descent algorithm. So what we have the function and then gradient of the function this is the gradient of the function, and then the steepest descent algorithm the steepest descent algorithm is given as follows. You have xk plus 1 is xk plus lambda k dk, where dk is negative of gradient of f at xk and lambda k is found by minimizing lambda k over f of xk plus lambda k dk. So this is how you find lambda k and dk. So let us apply this algorithm. This is our initial point x naught. So d naught is gradient of f at x naught, which is 1 and negative 1. So x1 is x naught plus lambda naught d naught. So f at x1 is as follows. So this is the function at x1, and minimizing f of x1 means that we need to find out the derivative and set it equal to 0. That means 2 lambda naught minus 2 equal to 0, which implies lambda naught equal to 1. So therefore, x1 is minus 1 and 1. Now this is the first iteration. We need to find out for the second iteration. So second iteration, for this we have x1 equal to minus 1 and 1. d1 is gradient of f at x1, which is minus 1 minus 1. And then x2 is x1 plus lambda 1 d1, which is equal to the following. And now we need to find the function at x2. This is just substituting the value. So simplifying it, just opening up these brackets. This is just plain and simple algebra. So now we need to minimize it. So minimizing f of x2 means that we need to set the derivative equal to 0. This gives us lambda 1 is 1 over 5. So lambda 1 is 1 over 5. Therefore, x2 is minus 1 plus 1 over 5 and 1 plus 1 over 5. Giving us minus 4 over 5 and 6 over 5. So the function's value at this point so this comes out to be, let us simplify. So the function's value at after the second iteration is minus 6 over 5. But unfortunately, this option is not given over here. So each of these options are basically incorrect option, and the correct answer is minus 6 over 5. So this was an incorrect question in the previous year's assignment, which did not have a correct solution. Next question. So let f be a function from R2 to R, and fx comma y is defined as x squared plus 4y squared plus 3x minus 4y plus 6. And then here we need to use Newton's method. Newton's method is an iterative process, starting with an initial guess and we need to find out the next first iterative point. So basically, with the initial point and then the next point, we need to find out using Newton's method. So just like we used steepest descent method to find out the minimum value of a function, Newton's method is used to find out the zero of a function, the 0 point of the function. The root of a function, so to say. So Newton's method so the algorithm is that xk plus 1 is xk minus Hessian matrix inverse times gradient of f at xk. So hf is nothing but Hessian matrix, or basically del squared f. So let us find out del f, gradient of f. Sorry. And then the Hessian matrix. Is the Hessian matrix. So from this we will get the matrix as follows. So the inverse, Hessian matrix inverse of a 2 cross 2 matrix is 1 over determinant of that matrix, and then you interchange the diagonal elements and multiply the off diagonal by -1. So this is the inverse, Hessian matrix inverse, and it is independent of the coordinates. So this is same no matter what your point xk is. So we have x1 equal to x0 minus Hessian matrix at x0 inverse times gradient at x0. So x0 is 0, 0. Hessian matrix inverse is the following, independent of the coordinate x0, and gradient of f at x0 is 3 and -4. So this gives me the following. And this is what they are saying is a and b. So that means a plus b is nothing but -3/2 plus 1/2, which is -1. So the correct answer is a plus b is -1. Next question, another question on KKT conditions. So using KKT conditions, the value of alpha for which the point 7/2, 9/2 is an optimal solution of the constrained optimization problem given as minimizing 2x squared plus alpha xy plus y squared minus 5x minus 2y under the constraints 3x plus 2y is less than equal to 20 and xy are positive numbers. So this is the constraint optimization problem that we have, and we need to apply the KKT conditions and find out the value of this alpha for which this point right here is an optimal solution. So let us copy our KKT conditions from one of the previous questions here right here. So this is the KKT conditions that we had written. I don't want to write it all over again, so I will try and copy this thing from here. I need to be a little bit skillful in trying to copy. Yeah, I think I've copied it properly. So let me write it maybe here. I think a little bit I've made it bigger. So these are my KKT conditions. Let me just rearrange some stuff over here. This is one constraint, and then the other constraints are that these numbers are positive. And let me get this guy here. Okay, better. So these are my KKT conditions. So what is my function? My function is as follows. And my first constraint, so according to the convention of this course, the first constraint which is significant over here is this constraint. So this is written as G. And then we have other constraints, which is basically stating the positivity of X and Y. So from the KKT condition, let us look at the first KKT condition. What do we have? We have gradient of F plus lambda times gradient of G plus mu1 times gradient of H1 plus mu2 times gradient of H2 is equal to 0. This is coming from this first KKT condition over here. So this means this is gradient of F, this is gradient of G, this is gradient of H1 and gradient of H2. So we get two equations from here. First one and then the second one. And then from this KKT condition, this one, we will get lambda times G is mu1 times H1 is mu2 times H2 is equal to 0. This implies that lambda times G is what? 3x plus 2y minus 20 is mu1 times H1 is what? Negative x is mu2 times H2 is what? Negative y, and this is equal to 0. Now since x bar and y bar, these optimal point is not equal to 0, so we get mu1 equal to mu2 equal to 0 from here. So this x and y is not 0, so mu1 and mu2 have to be equal to 0. And then the other condition is this one over here. So this implies, let us put in the optimal values. So what is this? This is negative 1 by 2 lambda equal to 0, which implies that lambda is also equal to 0. So now let us come to this equation, this first equation over here. So 4x plus alpha y minus 5 plus 3 lambda minus mu1 is equal to 0. So this implies 4 times x is what? 7 by 2, the optimal point. Alpha times y is 9 by 2 from the optimal point. Lambda is 0 and mu1 is also 0. So this gives me that alpha is negative of 2. So the correct option is option A, the value of alpha for which this point is optimal point. Now two more questions. The optimization problem of maximizing fx such that gx is less than equal to 0 is convex when we need to find out the conditions for convex problem. And we had a similar question earlier. So I will copy that condition for you from there. So this is the condition. For a convex programming problem. So a convex programming problem, which is of minimization type, is convex if f and g both are convex. And for a maximization type problem, it is convex when the function f is concave, whereas the constraint g is convex. So the correct option in this case is option D, that f is concave and g is convex. So for convex, g always has to be convex, and f is convex or concave depending on whether you have a minimization problem or a maximization problem. And in our case, we have the maximization problem. So now the last question. So we are given a function fx comma y is equal to x e to the power minus x squared minus y squared. And we have 2 points, negative 1 over root 2 comma 0 and 1 over root 2 comma 0. And we need to check whether these points are points of minima or points of maxima. And let us do that. So gradient of f is, so we need to use the chain rule to differentiate this function. So this is like a product of two functions, x being the first function and e to the power minus x squared minus y squared being the second function, first function, second function. So, and you need to apply the product rule, sorry, not chain rule, the product rule and then the chain rule as well, chain rule on this function to find out the derivative. So this is the gradient of this function. Let me simplify. So this is gradient of f. And for minimum or maximum, gradient of f needs to be equal to 0. So this implies that both del f by del x and del f by del y need to be equal to 0. And so from this, we get 1 minus 2x squared equal to 0. Why? Because exponential function is never 0. Exponential function never crosses the x-axis. It never becomes 0. So that means the term next to the exponential function, which is in product, needs to be 0. So from here we get this. And since x is non-zero, therefore we get y is equal to 0 from here. Now, del squared f we need to find out. Again, this is going to be like really cumbersome in the sense that you just have to keep differentiating, keep applying the product rule and chain rule over and over again. So let us do that. This is, I'm just differentiating and writing all these terms. So let me just simplify further. By taking the exponential term common. Just grouping the terms. So this is my del squared f. Now I need to find out del squared f at the point u. So we see that del f is 0 for both the points u and v. So del f at u and del f at v are 0 because these are the points. X is plus minus 1 root 2 and then you have minus 1 by root 2 plus 1 by root 2 and y is equal to 0 over here. So these are the points which satisfy del f equal to 0. So we need to check whether del squared f is positive semi-definite or negative semi-definite to decide whether it is point of minimum or point of maximum. So let us look at del squared f at the point u. So at the point u, we need to, so u is what? U is negative 1 over root 2 comma 0. So we get, so this first term over here, this 1 minus 2x squared, this is going to be 0 when x is negative 1 over root 2. So this is 0 plus e to the power minus 1 by 2 because x is negative 1 over root 2 and y is 0. And x is negative 1 by root, so this is minus 4 times x is minus 1 over root 2. So this is the first term in the matrix. Then we have 0 because 1 minus 2x squared, it's 0. Then again this term is 0, 1 minus 2x squared, that's 0. And then e to the power minus 1 by 2 times y is 0, so times minus 2 times minus 1 over root 2 because x is minus 1 by root 2. So this is giving me so this is a diagonal matrix. Now in diagonal matrix, the eigenvalues for diagonal matrix, eigenvalues are the diagonal elements. And these eigenvalues are greater than 0. Each of this term over here are greater than 0. Therefore, it is positive definite by the eigenvalue test. If all the eigenvalues are positive, then you have a positive definite matrix. And since del squared f is positive, therefore, u is a point of minimum. So U is a point of minimum. And let us similarly find out for V. So V is the point plus 1 over root 2 comma 0. So again, the first term over here, 1 minus 2x squared, that is 0. Then you have plus e to the power minus half times minus 4, and x this time is 1 over root 2 plus 1 over root 2. Then you have this 1 minus 2x squared, so that's 0. Then here 1 minus 2x, so 0. 1 minus 2x squared. So, and then over here y is 0, so negative 2 times 1 over root 2. So this matrix is this is again a diagonal matrix. Diagonal matrix meaning eigenvalues are diagonal elements, and these diagonal elements are less than 0. So that means it is negative definite matrix by the eigenvalue test, and therefore point V is a point of maximum. So for maximum and minimum, what you want is you want gradient of f to be equal to 0. And further, if del squared f is positive definite, then it is a point of minimum. And if del squared f is negative definite, then it is a point of maximum. So U is minimum, V is maximum. That means the correct option is option C, that U is minimum and V is maximum. So this solves this question. It was pretty much a little bit lengthier than previous assignments because of these algorithms. So whenever you have these algorithms, either the Newton's method over here, the Newton's method, or the steepest descent algorithm, steepest descent, and you have to do multiple iterations of it, you just have to keep on applying the algorithm over and over again and continue until you reach the desired iteration level, or your condition satisfies that it is less than the epsilon condition. So stopping conditions has been discussed in the lecture when you basically stop a given algorithm. That is when you come closer and closer to your required solution, and the tolerance level is said to be some epsilon, which is a small number. So this covers this week's assignment, which was based on optimization problems. The focus was on different kinds of optimization problems and different algorithms to be used to solve those optimization problems. So this concludes this week's lecture, and once again I'm putting up the YouTube link in the channel so people can go ahead and subscribe to the channel in order to revisit this video again. So yeah, thank you everyone.